Okay, good evening, everybody. Let's get started. Take a look at the assignments on Canvas. Lab 6 is due this Friday. Pre-Lab 7 and Lab 7 are posted, and I'll give a little preview of those this Wednesday. Next week is, let's see, that would be next week. Next Wednesday, the 28th, I plan to hold exam 2, and that will be during the class period. And I will send out details of this on Canvas. I'll send out an announcement in writing, but basically it's going to cover capacitors and inductors through transistors. So through what we finish up today and what you finish on your homework this Wednesday. And I'll get those solutions posted so you'll have study material, and I will be posting review problems for that. So I'll send an announcement on Canvas. If you have any questions after you see all the details on Canvas, let me know. And lecture, let's see, last lecture was 14. I'm going to get that posted tonight. So you'll see that up on the links. And then as always, if you have any questions or just want to talk about something during class, the class material, please unmute and we will we'll discuss it. And if we want to go into more detail, we'll talk about that during office hours. And otherwise, please stay muted to keep the background noise low. So this is the course roadmap, and what you see here is we've covered the circuits part of the course. We have covered through the semiconductors almost part of the course. We'll finish that up today. And so your exam 1, no, your exam 2 will be through semiconductors, through the transistor circuits. And today, after we finish transistors, we're going to move on to operational amplifiers. And so I'll give you an introduction and we'll start working those circuits. So what I'd like to do is continue on with the transistor circuit. Okay, so let's see, I just managed to pin, not what I wanted to pin. Okay, so this is where we left off last time. And we had this circuit with a transistor. Remember, a transistor controls its collector current using base current. And when the transistor is operating linearly, you get this relationship IC is equal to beta IB, or beta is some number. In this case, it's 100. That's actually the current gain of the transistor. We get this linear behavior as long as the transistor is not saturated. And when the transistor is saturated, we know that because the VCE value falls to about 0.2 volts. Excuse me. Okay, and so we have the circuit. I drew this circuit without this voltage source. And remember, when you have a node voltage written in at a node, like I do here at the top, it implies that I have some voltage source applied between ground and that node. In this case, it's a 5-volt source. So you can just assume it's there. In this case, I drew it in to help out with this Kvl equation down here. And so what we did is we wanted to make a table of IB, IC, Vx, which is the voltage across the resistor, and then VCE, the collector to emitter voltage. And so we worked each one of these rows by applying an IB, that was a given, an IB value, calculating an IC value, a collector current, and assuming linearity. And then we had to check that assumption by calculating VCE. And in order to do that, we had to calculate Vx and then use a Kvl equation in order to find VCE. And so we did that by starting at 0 milliamps, which we call cutoff, and then increasing IB a little at a time and watching what happened to IC and what happened to VCE. Eventually, VCE fell to 0.2 volts. And at that point, we're right on the border of saturation, right on the threshold. When I increased that current, IB, to 0.5 milliamps, what we found is that if you calculate using the linear equation for IC equals beta IB and then Vx, we found that VCE tried to fall to 0 volts, but we know that that can't happen. You can't have VCE fall because of this transistor's characteristics. You can't have it fall to 0 volts. We're going to assume it falls to roughly 0.2 volts. And then you can work backwards. You know that if you have 0.2 volts across VCE, then you must have 4.8 volts across the resistor. And then from that, you can use Ohm's law to calculate IC. So IC is actually not limited here by the transistor, it's limited by the resistor, okay, because of Ohm's law. And so we increased to 0.5 milliamps and we only got 48 milliamps, which is less than you would expect using the linear equation. So I wanted to point out you could also put even more current in. Let's put 5 milliamps into this circuit, into the base. So 5 milliamps. And you're not going to hurt the transistor by doing that. If you eventually, if you put too much current, like, I don't know, an amp, right, or something really big, you're going to heat up the transistor so that you'll damage it. But 5 milliamps won't do anything. Won't do anything bad. Let's assume linearity. I'm pretty sure we're not going to be operating in the linear region here, but let's assume that. So IC equals beta IB, if we're operating linearly, would mean that you have 100 times 5 milliamps, which is 500 milliamps, a half an amp, flowing into the collector. If we had 500 milliamps, 0.5 amps, flowing into the collector, we would have that also flowing through the resistor, the 100 ohm resistor, and we would have 50 volts, right? 500 milliamps times 100 ohms is 50 volts. If that were true, by KVL, we would have negative 45 volts, right? 5 minus Vx, minus 45 volts VCE. That can't happen. You can only have as low as 0.2 volts. So this isn't going to happen, right? I'm going to cross that out. You're going to have 0.2 volts here. And again, working backwards, you're still going to have about 4.8 volts, not 50 volts, across the resistor by KVL. And Ohm's law tells you that if you have 4.8 volts across a 100 ohm resistor, you're going to have 48 milliamps. Okay, so we've reached what we call saturation. And we talked about this with the fluid flow analogy. That valve is all the way open. It's as far open as you can get, and it's not going to open anymore. And so all the current that can flow is flowing, and you can get no more current flowing into the collector by applying more base current. So if I were to divide these into, let's say, regions, I'm going to call somewhere right here, this is saturation down here. Okay, and then up here, so that's this region. And then up here, this is linear. And then, of course, 0 milliamps for base and collector is cut off. So let's notice something here. We have a way to control a current with a smaller current, and that's an amplification function. So in the linear region, this transistor circuit is acting like an amplifier. It's taking a small current, and you could create a small voltage or create a small current using a small voltage over here. I'll show you how to do that. And you're amplifying that small current or small voltage to get a bigger current or a bigger voltage, and that's an amplifier. In the saturation region, we usually consider the transistor acting as a switch, and we will work an example circuit where a transistor acts as a switch. And in other words, typically, this input of current would be from something like a microcontroller, like an Arduino or other microcontroller, maybe through a resistor. But you would either apply a voltage, maybe 5 volts, or another voltage, 0 volts, again through a resistor here, to cause current to either be in cutoff or saturation. And at that point, you're either letting all the current flow that can flow, right, happen, or cutting the current off. So that's what I mean by acting like a switch. Okay. If you remember in the circuits part of the course, when I talked about the different types of sources, the controlled sources, we had for example, a current-controlled current source. Well, if you look here, you can actually see those types of sources happening. Here, I have a current IC that is controlled by IB, right? So IC is controlled by IB. That's how we described a current-controlled current source. Here we have a voltage, Vx, being controlled by IB. Okay, that would be a current-controlled voltage source. It's a voltage source, right, acting like a voltage source, and it's controlled by this current. So that's what I meant by you have some voltage in a circuit that is controlled by some other variable, like some other current. So this would be a current-controlled voltage source. You've got another voltage that varies in a different way with current over here. Okay, so you could use this current IB to control VCE. You could also think of putting a voltage source out to the left through a resistor to control that current IB. And so you could have a voltage-controlled current source or a voltage-controlled voltage source. So all 4 of those sources, those controlled sources, could be built using just one transistor and one resistor. Okay?
Professor?
Yes.
I think you did go over this last class, but can you just repeat why the transistor circuit can only go down to 0.2 volts for the VCE?
Yeah, it's a property of the transistor, and it's limited by the voltages, the junction voltages of the silicon in the transistor. Remember, that's an NPN transistor, so you have 2 junctions in there. And what you'll see if you did a KVL from base to emitter to collector back to base, you would find that you actually start forward biasing the base to collector junction. We don't usually talk about that, but you start actually forward biasing that junction when you approach saturation. And that has the effect of, well, the transistor no longer operates linearly. That voltage where that happens is where VCE is about 0.1 to 0.2 volts, somewhere in there. But we usually use 0.2 volts as an approximation for design purposes and analysis purposes. And it gets you pretty close. Does that answer your question?
Yes, thank you. And it looks like a question just popped up in the chat about it too.
Oh, let's see. Is 0.2 volts a property across all transistors? Transistors vary. That's common for silicon transistors, right? You can look at other types of semiconductor transistors. If you have a silicon transistor, it's going to be around, again, 0.2 volts. If you look at the transistor data sheet, in fact, you have the data sheet for the transistor in your kit. It's linked on Canvas. You can take a look at what the real value would be, and it varies a little bit. It varies a little bit with the collector current, and so it changes a little bit around 0.2. But if you really need that value, you look at the transistor's data sheet, and it has a plot of IC versus VCE for different IB values. Okay. All right.
And Professor, sorry, can you say again how the saturation state acts as a switch? I kind of heard like the last part of it, but could you just explain it again?
Sure. In fact, we're going to do an example next, and let me do that next example, and then if you have any questions about that, we'll address it then. How about that?
Thank you.
Sure. Okay. So I'm going to take this away. So what you're going to do in this class, we're going to concentrate on that function where you use a transistor as a switch. This is really common if you want to hook a device, connect a device to a microcontroller, where you have, let's say, a pin on that microcontroller where you can either output 0 volts or 5 volts. And maybe that pin can only supply a milliamp or two, or maybe a few milliamps. And let's suppose you want to control a device, maybe a small motor that requires 200 milliamps. So you need some kind of interface between the controller, right, that microcontroller pin, and the motor so that you can control a lot of current with just a little current, right? So that should sound familiar. So let me write out the problem. I'll draw a schematic here, but we're going to design a circuit, a transistor that acts like a switch. And we're going to find a collector resistor. So that IC equals 25 milliamps. When Q1 is the transistor. Is saturated. This will make more sense when I draw the circuit. And then we're going to find the base resistor, RB, so that Q1 is saturated. When we apply an input voltage, Vin, of 5 volts. So this is just like that microcontroller example. So let me draw this out here. If you have a node up here with 5 volts supplying voltage to the circuit, and I'm actually going to put a diode in here also. Assume this is a light emitting diode. You want this diode to light up. Okay, and so you have a transistor. It's controlling current through its collector. So that's IC here. And you're controlling that current with the base current, IB. And the base current is actually being controlled or produced by some voltage source out here. So this Vin could either be 0 volts or 5 volts. So that would be like the output of some controller. that could only output just a little bit of current, and you want to control a lot of current to light up that LED really bright. Let's talk about that LED. Diode D1 is an LED, light emitting diode, and it has a forward voltage equal to 1.8 volts. So that's not 0.7 volts. That's not just a regular silicon diode. It is a light emitting diode. And depending upon the color of the LED, you'll have different forward voltages. Okay, so in this case, you look at the LED data sheet. This is probably a red LED. And you would see that when there's 25 milliamps flowing through this diode, you have about 1.8 volts forward voltage. So that's where this 25 milliamps comes from. The LED data sheet might say this LED is designed such that it's at full brightness at 25 milliamps. Q1 is a transistor. Let's say it's a silicon transistor, right, Si. And it has a beta. You can find this in the data sheet. You can find a range of betas actually in the data sheet, and it's 100. We're going to say VCE saturation, VCE sat is equal to 0.2 volts. Again, you could read that off of a plot in the data sheet. It'll be about 0.2 volts. And then VBE, again, you could look at the data sheet, but you would find for a silicon transistor, you'd have about 0.7 volts between base to emitter across that diode junction when there's current flowing into the base. Okay.
Professor McCurdy,
I'm sorry?
is the ground always at that emitter?
It doesn't always have to be at the emitter. In the circuits we're going to work with, it's going to be very common for it to be at the emitter.
Okay, so if it doesn't say, we can just assume that that's ground?
No, it'll say. The circuit will show a ground in it if I'm using node voltages. So yeah, this will be shown. If you didn't see this here, it would be somewhere else, but most of the time, if not all the time, it's going to be here.
Okay, I was just wondering because on the homework, I don't know if it could show it and I just missed it, but I don't remember it showing ground being there.
Okay, so another way that this could be shown, let me show you what this implies. I'll erase, well, I don't have to erase this. Let me do this. This will help with our KVL. So you might see just a source here like that. Because remember, Vin is a node voltage here, and that implies that there's some source connected to ground. And then the same thing here. I could draw a source right in here like this, 5 volts. So if I don't have any node voltages that I need to reference, I could delete this ground. I have not changed the circuit whatsoever because for all the node voltages, I've explicitly put in sources. But when I was using just Vin over here as a node voltage and 5 volts up top, I would have to put a ground there.
Okay, that makes sense. Okay. Thank you.
Sure. Okay, so here's what we want to do. We want to find the collector resistor value in ohms so that when Q1 is saturated, right? Q1 is saturated when I apply a voltage over here, according to B. So when Q1 is saturated, I want 25 milliamps flowing through that resistor and also that LED so I can light it up. Okay, so let's figure that out.
Professor?
Yes.
Why is it that we wrote in that Vn is either 0 volts or 5 volts?
So what I'm designing here is a circuit where Vn will be either one of these. And what I want to do is when Vin is 0 volts, I want the LED turned off. There's no current flowing through it. When Vin is 5 volts, I want the LED turned on so that 25 milliamps is flowing.
Okay,
Does that make sense?
Yes, thank you.
So that's what I mean, that this transistor is acting as a switch. It is acting to either cut off current through that light emitting diode or to allow a certain current to pass through that diode. So when the input voltage over here is 0 volts, the switch is off. No current is flowing. When the voltage over here is 5 volts, the switch is on. Current will flow through that LED. Well, so why don't I just connect V in right to the LED, right? Well, I'm assuming like a microcontroller could not output out of one of its pins 25 milliamps typically. It could output maybe 3, 4, 5, maybe 8 milliamps, but you'd be stretching it to get that much current. So to be able to control a lot of current with a little current, that's what a transistor does, right? I'm using this transistor as a switch. So I'm either going to have the transistor in cutoff, that means the switch is off, or I'm going to saturate the transistor and allow current to flow. Okay. So what I'm going to do here is I'm going to write a KVL equation because I think this will work. What I want to do is find out when current is flowing, when Q1 is saturated, I want 25 milliamps flowing through that resistor. And I need some resistor value in ohms to force that to happen. When the transistor is saturated, I have 0.2 volts approximately across VCE here. The voltage across this resistor, when current is flowing by Ohm's law, is IC times RC. Right? And then the current across this diode, I'm sorry, the voltage across that diode is VD. Okay. So let me write a KVL equation. Again, I think I have a known voltage VD. VD is going to be VF when current is flowing. VCE is going to be 0.2 volts when the transistor is saturated. I know what I want my IC to be, 25 milliamps. So RC will be the only unknown here. So if I write this KVL, let's start down here and go around counterclockwise. I would say -5. Let's see, -5 plus VD. -5 plus VD plus ICRC. Plus ICRC plus VCE equals 0.
Is the homework really similar to this?
Yeah, it's really similar to this.
Because this seems pretty familiar.
Yeah, it should look really familiar if you've looked at the homework. Okay, and so now let's rearrange this. Let's see. Let me move ICRC out. ICRC equals 5 minus VD. 5 minus VD minus VCE. And I'm trying to find RC here. So RC equals 5 minus VD minus VCE over IC. Okay. So now we can fill in some values. 5 volts, that's the power supply value. VD, we know we have current flowing through the diode. So VD equals VF for that diode, 1.8 volts. VCE, we're assuming the transistor is saturated here. That's when the LED is on. So that's it. I'm not going to write that V. Minus 0.2 divided by IC. That's the current that we want. 25 milliamps. Okay. So we get RC equals 120 ohms. If you work that out on your calculator. Okay. Any questions how I got that answer from the KVL?
Out of curiosity, if you didn't draw in the fake voltage sources, how would you envision going through that KVL?
Well, I actually, without drawing the source, I actually envision the KVL kind of the same way. I'm going from, I imagine going through a source. So if I erase that source, when I go from ground up to 5 volts, I imagine going through that negative side of the source.
Okay, cool. Yeah, I didn't know if you could just like do it going down the line, but that makes sense.
Yeah. And if you go the other way, you know, minus VCE, minus ICRC, minus VD, then you have to say plus 5 volts down to 0.
Cool.
Professor,
Yes.
what is that note that you have like in the little just sort of area where all the descriptors are, like D1 LED? What does Q1 mean?
Oh, Q1 is the transistor. So just like we use R for a resistor and D for a diode, Q is the symbol we use for a transistor.
Oh, so that's silicon then. Is what that
It's any transistor. It could be germanium, but Q.
Well,
Oh, I'm sorry.
Yeah.
You're asking about this.
Yeah.
Yeah, Si, silicon. That's right.
Oh, okay, gotcha. Thank you.
So basically for something like this, if you're doing it very quickly, you can just look at the given voltage and just think that in KVL that would be negative of what is given. For the
If you go
reasons
in
we
this direction,
described.
yeah. Mm-hmm.
Yeah.
Yeah.
Right.
Yeah, if you know, for the first couple times you do this, you might draw in the source, so you get a feel when you come from 5 volts down to 0, let's say 5 volts down to ground, to know that you put a plus in. I envision the source being there when I do that, so even though I don't draw it, it helps with those signs. So let's solve for now. Now we've solved for RC. We have to solve for RB. Okay. And I'm going to use another KVL equation here, except around a different loop of the circuit. So let's go around this bottom loop. I know my voltage Vin. I know it's 5 volts when I want the transistor saturated. I don't know RB, but I do know that this voltage here is going to be IB RB, right, with IB going into the left of that resistor. I know that I have a voltage here when current is flowing, when IB is a positive value there. This is going to be VBE, and we know that value when current is flowing. And so I think I'm going to have everything I need to solve for RB. So let's write that KVL minus 5 plus IB RB plus VBE, right? I went from the base node to the emitter node, so that would be VBE. And now I'm back to the starting point, equals 0. Okay, so I can solve for RB. RB is going to be 5 minus VBE over IB. All right, so let's figure this out. So I know VBE, it's going to be 0.7 volts. I have to figure out what IB is going to be. Let's talk about that. So we know that Q1 is saturated. So in saturation of this transistor, we know that IC is not going to be as high as it would be if the transistor weren't saturated. In other words, IC is going to be not equal to, but less than beta linear IB. And I call it beta linear here because we know that when the transistor is operating linearly, beta is equal to 100. You might consider beta actually falls, because if beta is equal to IC over IB, then beta actually falls as the transistor goes into saturation. For the purposes of this analysis, we're just going to say when the transistor is operating linearly, beta equals 100. But in saturation, IC is less than 100 times IB because the valve is already all the way open and you can't get any more current through IC, the metaphorical valve. Okay, so what this means is that IB has to be greater than some value. IB has to be greater than IC divided by some beta, linear. Okay. So I can choose any IB I want as long as IB is greater than, let's see, IC 25 milliamps over 100. Okay, so IB has to be greater than 0.25 milliamps, 250 microamps. Here is where you can use some engineering judgment to choose a value of IB. We know IB has to be greater than 0.25 milliamps. That's a given. So what about 0.26 milliamps? Well, that might work. Let's talk about some practical considerations of a transistor. So for a homework problem, it would work just fine if you used 0.26 milliamps. But in the real world, the beta of these transistors vary from transistor to transistor, lot to lot, over temperature, and you can actually find that data in the data sheet. So this transistor might have a range of maybe 75 to 150. So you might be conservative and say beta equals 75 if you saw a range, just to get your beta right, your current right. So what I'm going to do here is I'm just going to put an engineering factor here. I'm going to choose IB equals 1 milliamp, because that will give me a factor of 4. If beta fell to about 25, then I would still have the transistor saturated. Okay. This is up to you. So in lab, you're going to be able to choose whatever value you want. So why wouldn't you choose a bigger value, 10 milliamps, 20 milliamps? Well, first, your source might not be able to supply that much current. And second, if this is a battery-powered device, you're just wasting power. You're shortening your battery life. So you really want a small current for battery life, and you want a large current to make sure your transistor goes into saturation. So again, another one of those engineering decisions. There's no one right answer. There are only options. So I'm going to choose IB equals 1 milliamp. You could choose 2 milliamps, you could choose a half a milliamp, it'll probably work. So RB equals 5 minus VBE 0.7. Remember, VBE is 0.7 when current is flowing into the base, divided by 1 milliamp equals 4.3 k ohms. And that's RB. Okay, so if I make this resistor 4.3 k ohms, and if I make RC, this resistor, 120 ohms, then when I apply 5 volts at V in, I'll have 25 milliamps flowing through that LED. It'll light up nice and bright. When I apply 0 volts to the input, I'll have 0 IB. The transistor will be in cutoff. The LED will turn off because no current flows. IC would be 0.
So,
okay.
Yeah. So in the homework, when it said for like the problem that's like find, in this example, it would be RB, so that current going through is 1 milliamp. Is that basically just this step done for us on the homework? Just like,
Yeah,
or is
well,
that giving away too much?
in the homework, I think it says whether the transistor is saturated or not. I think you have one problem where the transistor is saturated and one problem where it's not. So if the problem says the transistor is saturated, you can assume that VCE is 0.2 volts. Okay? If it says the transistor is not saturated, then you don't know VCE until you figure out the current IC and then do a KVL.
Right.
Okay.
I'm just more asking, we're given like a scenario for when the current flowing through RB is greater than the one found. So, and us being given that is basically just sort of the choosing phase done for us, right?
Right.
Okay.
It, you know, you can come at this problem from a couple perspectives. This was designing for those resistor values. You could also ask the question, if I were given resistor values, what voltage V in would saturate the transistor, right? And so there you'd have to figure out, okay, what IC, just like we did in the previous problem previous slide or whiteboard where I drew out that table, I had to figure out, okay, VCE falls to 0.2 volts. What current is that IC based on a KVL equation? And then what IB do I need to cause that IC to happen to put it right on the threshold of saturation? And then you can figure out the voltage. So you can come about this from any direction, really.
Okay.
Professor,
Yes.
can you explain a little further, like where the actual voltage VBE is referring to? Because I was kind of wondering about that last lecture too, of like where the plus and minus actually are referring to.
Yeah, sure. Okay, so the if you put your voltmeter here, right, your red lead there of your voltmeter, or your positive lead, and you put your black lead there, right, that would be VBE.
Okay, thank you. And so the little note of VBE equals 0.7 volts when IB is greater than 0, is that something that we would just get from the data sheet?
Yeah, it is. You would know what VBE is. VBE actually looks like a silicon diode, where this is the base, this is the emitter,
Oh, okay.
right?
So
And
that's one of
so
those. Oh, sorry, go ahead.
yeah, and so it looks like that characteristic where this is VBE, IB, and this is about 0.7.
Oh, okay. All right, thank you.
Sure. Okay, other questions about this? Okay, so you'll see those problems on homework. So transistors can be used, obviously, here as a switch. They can also be used as an amplifier that you saw an example of, where you saw the table that I drew for the previous whiteboard segment. You could use a little current, right, a little IB, or in this case, a little voltage to change IC, or in this case, maybe ICRC a lot. And that's what an amplifier is usually meant to do. It's meant to take a little voltage or a little current and multiply it up to a bigger voltage or a bigger current. Think about maybe a microphone going into a PA system, so that you have a big voltage at a speaker from a little voltage at a microphone. You can do that with a transistor. Typically, when you need a lot of gain, or the ratio of voltages, you will have many stages of transistors. You can make an amplifier out of one transistor, but if you need a lot of gain, you would use multiple stages. There is another way to do this. There are integrated circuits that use transistors to create amplifiers on a chip that are specifically meant to, well, basically make your design life easier. So what I'm going to do now is we're going to go from single transistors to integrated circuits. And I'm going to step you into op amps now. So let's talk about operational amplifiers.
Professor, I had one more question about this.
Sure.
I'm still not quite sure how this acts as a switch. Is it just because we're talking about when it's saturated, and then when would the switch be, like, quote unquote off?
Okay, so it's really an electronically controlled switch. So this switch is controlled by either applying 0 volts or 5 volts. Okay, so if you apply 0 volts here at Vn, this electronically controlled switch, I would call it off, because no current flows. When you apply 5 volts at Vn, this transistor allows current to flow, and so it turns the LED on.
Oh, okay, I see. Thank you.
And the two states of that transistor are either cut off or saturation. So that's why we say the saturation mode of a transistor is usually used as an electronically controlled switch.
Could you use like a square wave input, like AC current as the switch there?
Like at VN?
Yeah, if you had like -5 volts through there, would that not be able to flow through VBE?
Oh, if you have -5 volts, that you would not do that. What that would actually cause a, let's see, probably, what would that cause? Actually, no, that you would get no current flowing. If you apply negative voltage here, you would reverse bias both of these junctions. So yeah, you'd be fine. Typically, if you were going to apply a square wave, again, you could go negative, but typically if you were going to, let's say, flash this LED, you would apply a square wave that varied between 0 volts and 5 volts, just like you did in your RC circuit lab, and you could flash that LED. In fact, if you used, remember you did pulse width modulation, we're going to talk about this later, later in the course, you could pulse width modulate the current through that diode by changing the duty cycle of maybe, a 1 kilohertz square wave, change the duty cycle to control the brightness of that LED. And you would actually have kind of like your headlamp, your, one of your Petzl or whatever headlamps, that's LED. You could control the brightness with the duty cycle. Duty cycle, that's what your headlamp does. Okay. All right. So what I'd like to do now is talk a little bit about op amps. Okay, so op amp stands for operational amplifier. And this is an op amp, the schematic symbol of one anyway. And it's a 5-terminal device. So we've got 5 terminals here around this triangle. And I would define an op amp as an integrated circuit. It's a set of electronics on a semiconductor chip. So what's a semiconductor chip? Semiconductor chips are these die. This is a die. It's called a silicon die, usually made on wafers. So this is a wafer that has many copies of that die. That wafer is cut up into these dies physically, and then that die, because it's so small, this is not to scale here, that die is so small with little pads on it that it's put into a plastic package when you want to use it, let's say, on a breadboard. So this has a tiny little silicon die in it with wire bonds that go to each one of these metal leads on it, metal pins. Okay, so that's physically what it is. It functions as a high gain differential amplifier. Okay, high gain means it multiplies a little input by a big value to get a bigger output. Differential means that this amplifier considers 2 voltages, takes the difference, and amplifies the difference. On the left side, as this is drawn here, I have the inputs of the op amp. So these 2 terminals here, these 2 leads are the inputs. On the right side, I have the output of the op amp. Okay, let's talk about the inputs. The input on the top here, and it's actually not necessarily always on the top, but the input associated with this plus. This plus is an indicator for this input here. And that plus indicates that this is the non-inverting input. It's just the name of that input. We're going to call that voltage V1. So V1 is the voltage of the non-inverting input. It's the input next to the plus sign. The other input next to the minus sign is the inverting input. We give that a voltage variable V2. Okay. At the output, we've defined just a V out voltage. So that's the voltage at the node voltage at the output of the op amp. Okay. this terminal up top is the positive supply voltage. We're going to call it VCC, right? So this is V sub CC is the positive supply voltage. Down at the bottom here, this is the negative supply voltage. We're going to call that voltage VEE, okay? The relation, so these two voltages actually supply power to this amplifier. They power the amplifier. V out is related to the input voltages by this equation. It's really straightforward. V out equals some number times the difference between the two voltages, V1 minus V2. AOL is called the open loop gain. That's what the OL stands for. It's the open loop gain. We'll talk about closed loop gain later, but it's the open loop gain. It's typically a big value. It's 10 to the fourth, 10,000 to up to near 1 million. Okay, so that's the range. So that's a big value. It's a big value multiplied by a voltage difference. That's why an op amp is a high gain differential amplifier. Multiplies a difference in voltages by a big number, gives you an output. There's another way to express this. We're going to define a voltage value called VID, and I'll show you that on the next slide when we get there next time. VID is actually the voltage between the two inputs. It's V1 minus V2, right, working with node voltages. So V out is actually AOL times VID, AOL times the input differential voltage, okay? All right, so there's your really quick intro to operational amplifiers. We will continue looking into op amps, what they are and how they work and how to analyze them next time. Okay, so in closing, let's see, it's 1 minute past, I should have ended. Let's just remember that Lab 6 is due this Friday, and take a look at pre-lab and Lab 7 on Canvas. I will send out information on the exam next Wednesday, or for next Wednesday. I'll send that exam information out before the next class. And I'll also send out details on the review problems on Canvas. So thank you for joining the class. I'll have office hours in a minute or two, and I hope it's working out well. If it isn't, please let me know. And if I don't see you at office hours, I will see you next time.